Hello everyone, welcome to BADM A724 Quantitative Methods and Business Analytics. This is Lecture 10. I'm your instructor, Dr. Frank T. Shea. In this lecture, we're going to cover ANOVA, analysis of variance, especially the one-factor ANOVA. We'll talk about multiple comparisons, test for homogeneity of variances, and also we're going to cover Monte Carlo simulation. Okay, overview of ANOVA. ANOVA, what is ANOVA? ANOVA, or analysis of variance, is a very useful tool. It's a comparison of means. Basically, ANOVA allows you to compare more than two means simultaneously. Well, if you want to just compare two means, you can use hypothesis testing that we covered in lecture 9, right? But if you want to compare like 3 or 4 or 5 or even more means, group means at the same time, you need a better tool. ANOVA is such a tool that you can use. Okay? Proper experimental design efficiently uses limited data to draw the strongest possible inferences. It's very quite powerful. Okay? The goal of ANOVA is explaining variation. Okay? ANOVA seeks to identify sources of variation in a numerical dependent variable y. It's also called the response variable. Variation in y about its mean is explained by one or more categorical independent variables. We call them factors. Or is unexplained. We call that part, the unexplained part, the random error. Okay? And basically, we look at the variations in y around this mean, up and down from this mean. Variations, we can separate that into two parts. One part that can be explained, due to certain factors, and the other part cannot be explained, unexplained variation due to random error. Okay? Each possible value of a factor or combination of a factor is a treatment. We call them a treatment. We test to see if each factor has a significant effect on y using the hypothesis like this one. H0 is mu1, mu2, mu3, mu4. They're all the same. They're all equal. That means the four groups, in this case, four groups that we're comparing, they all have the same means. For example, if you have your company, your business has 4 factory locations, right? You want to see if the product they produce at each of the 4 locations are the same, or same with regard to quality, with certain features of the product. See if they are the same. They are similar or the same or not. Or maybe one of the factory location is doing better than others, or one is doing poorer than others. Right? So using ANOVA, you can find that out. Right? That's HO. H0 is mu1, mu2, mu3, mu4 are all equal. Right? H1 is not all means are equal. If at least one of them is not equal, then we conclude H1. Right? The test uses F distribution, and we have covered many distributions. Now this is the F distribution, and if we cannot reject null, we conclude that observations within each treatment have a common mean mu. Okay, we cannot reject null. They have a common mu, so they are pretty much similar. Yeah. Like the example I give you, for one factor ANOVA, okay, the dependent variable here in this case is the defect rate of machines or gadgets produced in this company. The defect rate is the dependent variable. That defect rate may be affected by one independent variable, which is a categorical variable, which is the plant location. the company has 4 plant locations: Lee's Bluff, Cacktown, Johnstown, and Goysville, right? A1, A2, A3, A4. And the factories and plant locations. Basically, we're examining to see if the defect rate is same across all 4 locations, or maybe one of the factory location is doing better or worse than the rest. Okay. For example, in one factor ANOVA, we test the hypothesis that the length of hospital stay, another example, right, is affected by the type of fracture. Right? We know that if someone suffers a bone fracture and then goes to a hospital, and doctor will check, and will tell him, how long you have to stay in the hospital to get the bones, fracture healed. Okay? Obviously, how long you stay in the hospital is affected by the type of fracture. If you have, I guess you have a hip bone fracture, you probably can stay. You only need to stay for maybe, I don't know, a week. You have a skull bone fracture, you may have to stay for a month or 2 months, right? So that's one factor ANOVA. But then we can do a 2-factor ANOVA. It will test this hypothesis. The hypothesis, the length of hospital stay, LOS, is affected by the type of fracture, just like above, and also the age group. Right? Length of stay is a function of type of fracture and age group. Maybe for the same time fracture, for a young person could stay, shorter than an old person. Okay, so age of the patient is another factor. We can also test for the interaction between the factors. Okay, so to summarize, for one factor ANOVA, in this case, the length of hospital stay is in hours may be affected by the type of fracture: facial bone fracture, radius fracture, hip fracture, other lower extremity, or others. Okay? Or you can look at with 2-factor ANOVA, you can look at the length of hospital stay affected by the type of fracture as well as age group. If the person is under 18, 18 to 64, or 65 and older. Okay? This will be 2-factor ANOVA that we can look at. Okay? There are assumptions of ANOVA. Right? ANOVA assumes that the observations on Y are independent. Okay, all the observations on Y are independent of each other, and also the populations being sampled are normal. Okay? And also population being sampled have equal variances. Okay? These are the assumptions, but ANOVA is somewhat robust to departures from normality and equal variance assumptions. So, calculations. You can calculate ANOVA using software like Excel. I want you to go to your Excel, go to analysis tools, right? And you go to ANOVA and try to play with that. Okay, you can use ANOVA Megastat. There's another software to do that. Minitab can do that. SPSS, they're all similar, in doing that. Large sample increases the power of the test. That we all know. We know already, right? But the power also depends on the degree of variation in Y. Okay? Lowest power would be in a small sample with high variation in Y. So, data format. When you enter the data in an Excel spreadsheet or other software, you can enter it both ways. 1-factor ANOVA only compares the means of C groups, right? And then you can consider the format of 1-factor ANOVA with the C treatments, with A1, A2, AC, the treatment. You can enter the data in columns. This A1, A2, A3, all the way to AC, that's treatments, and then the observations in Y. Right? For example, for the length of hospital stay, A1 should be like, say, facial bone fractures. And then you have the first patient with facial bone fractures stay in the hospital for how many days. And another person, another days, some other days, etc. And A2 will be a second type of fracture. like a hip bone fracture, and the patients all suffering from hip bone fractures have stayed in hospital for a different number of days. Okay, you can go like that, the data in columns. Okay, and you have N1 observation, N2 observations, etc. All the N1, N2, all the way to NC, they don't have to be equal. That's the beauty of ANOVA tool. You can have different number of observations in different treatment groups. Okay. Or you can enter data in rows like this one. Well, A1, the first type of fracture, enter the number of days, over here. A2, A3, A4, etc. Okay. Data format, sample sizes within each treatment do not need to be equal. So do not need to be balanced. That's good. The total number of observations equal to N equals N1 plus N2 plus N3 all the way to NC. The hypothesis to be tested here is mu1, mu2, mu3 all the way to mu c. That's all different groups, right? Different type of fractures. We want to see if the mean is the same, right? If they all stay in the hospital for the same number of days or weeks, and that's what we are trying to test to find out. And H1 is not all means are equal. ANOVA test all means simultaneously, and so does not inflate the type 1 error. Okay. One factor ANOVA is actually similar to a linear model. We'll talk about linear regression later on, but an equivalent way to express the one factor ANOVA model is to say that the treatment J came from a population with a common mean of mu plus the treatment effect A plus the random error. So the Y, the dependent variable, equals mu plus the treatment factor plus error. That is, how long you stay in the hospital, Y, there is a common mu, and then plus, a treatment factor that could be, like say, facial bone fractures, and you probably add 2 more days. If hip bone fractures, you minus, 5 more days, etc. Right? So you can express the same thing using a linear model like this to analyze. Okay. Excuse me. Random error is assumed to be normally distributed with 0 mean and same variance for all treatments. That's the assumption of ANOVA. A fixed effect model only looks at what happens to the response for a particular level of factor. We look at the A1, A2, A3, look at the factors affecting the length of hospital stay, the Y, the dependent variable, and see if they're all 0, right? They're all 0, there's no effect, right? If not all are 0, then there's the effect. Okay. If rationale is true, then the ANOVA model collapses to this. No effects then. Okay. Group means. Basically, for one factor ANOVA, this is how it works. Okay? First, we calculate the mean of each group. Mean of each group is calculated like this: yj bar. That's a dependent variable in j's column. That's the j's group. That's different. One type of fracture, for example. Okay? The average of that, length of hospital stay of that, equals yij. That's all the length of hospital stays within that group of J, and we add from first one to last one and divide by n. That's the mean of each group. And the overall sample mean, what we call the grand mean, can be calculated as this: y bar, overall mean, equals 1 over n. The yij first, is summed up from the first one to j's one in the j's column, and then from first column to c's column. So basically sum of everything, all the ones in the one column, and then in the different columns. Okay, so it's the same as nj times y bar, like this one. You introduce this here. Okay, that's overall sample mean. Okay. To analyze this, we need to partition the sum of squares. Right? For a given observation of Yij, the following relationship must hold true. Yij minus Y bar equals Yj bar minus Y bar plus Yij minus Yj bar. What do they mean? Right? Y bar is the overall grand mean. That's the of the dependent variable. Yij is the individual observation. So the difference between the individual observation and its overall mean can be rewritten as these two. Right? This one here is the Yj bar, that's the mean of j's column, minus the overall mean, plus Yij minus Yj bar. If you open the parentheses, you can see this two, this one here, and this one cancels each other. What you have left is this minus that. That's the same as this. So this equation holds true, right? And what's this then? What's Yij minus Y bar? Yij minus Y bar, this. That's deviation of observation from the grand mean. Deviation of each and every observation from the grand mean. And this one here, sorry, I'm missing the bars here because the software is a deviation of column mean from the grand mean. This is the column means, this is grand means. So that's a deviation from column mean from grand mean. We call that between treatment, right? Because this is contributed from the different type of treatments, the treatment group, different J group. And this one here is the deviation Yij minus Yj bar, deviation of the observation from its own column mean. So that's the deviation of each observation from its own column mean within the same column, within the same treatment group. We call that the within treatments. Okay, so this one between treatments, this one within treatments. So the deviations can be separated into two parts, within and between. Okay. And the same relationship is true for sum of square deviations, yielding the partitioned sum of squares. If you do a sum of squares, you can do the same. Okay? This is total sum of squares. This is sum of square between. This is sum of square within. We call this sum of square total, SST. We call this sum of square A, that's due to its factors, different factors. And then sum of square E, or SSE, sum of square error. Okay, basically we partition the sum of squares the same way. So SST equals SSA plus SSE. Okay. So sum of squares total here, and then sum of squares between treatments here, SSA. That's the part that's explained by factor A, right? That's the variation explained by the factors. And then there's the sum of square error within treatment. That's unexplained random error within the group. Okay. And SSA and SSE are used to test the hypothesis of equal treatment means by dividing each sum of squares by its degrees of freedom to adjust for the group size. So these ratios are called the mean squares, or MSA and MSE. Right? And then with MSE and MSE, we can calculate test statistic in F distribution, which is MSA over MSE. F equal MSA or MSE. Okay? Basically, this is this table summarizes everything. Basically, the source of variation could be a treatment between groups or within groups. That's error. Then sum of squares, you have sum of square A, SSA, that's between group treatment, SSE, that's error, and SST, that's total. Right? The degrees of freedom for each, for this one, since we have number of C groups, right? C groups in total number, 1 through C. Right? So degree of freedom here is for SSA is C minus 1. Degree of freedom for SSE is N minus C, and the sample size. C is the number of treatments, and degrees of freedom for SST is N minus 1. The mean squares is calculated by SSA over degrees of freedom. SSA, this is SSA over C minus 1. Okay? And then MSE, mean square error, this is mean square treatment. Mean square error is SSE here over its degrees of freedom in minus C. And then we can calculate F statistic. That's MSA divided by MSE. When we calculate that, once we calculate that, we can look at the table to find the critical value of F at a certain confidence level. Then we can determine whether we can reject null or have to accept null. Okay. In Excel, I want to give it a try using that. Remember, you go to data analysis, the tools, and you'll see the ANOVA as the first one, single factor ANOVA. You click OK, and then you can start to use it. Test statistic. F distribution, as we said before, describes the ratio of two variances. The F statistic is the ratio of the variance due to treatments, MSA, to variance due to error, MSE. Okay? F equals MSA over MSE. MSA equals SSA divided by its degree of freedom, which is C minus 1, numerator degree of freedom, and SSE divided by its degree of freedom, but DF2 is N minus C, that's denominator degree of freedom. Okay? When F is near 0, then there's a little difference among treatment. We not expect to reject the hypothesis. Okay? And F cannot be negative and has no upper limit. For ANOVA, F test is a right-tailed test. And you can use appendix F or Excel to obtain the critical value of F for a given level of alpha. Okay? This is the F distribution. Okay? This is the F curve, F distribution. You can see the long tail is to the right. Okay? So this is a right-tailed test. Okay? And you use the table at certain confidence level, right? You can determine your alpha and find F critical. Okay? And then using F statistic, you calculate from MSA over MSE, you find the ratio of F. If F is in this region, the blue region here, larger than F critical, you reject null. If less than that, you do not reject null. That's how we test the ANOVA. Okay? So the steps in performing one factor ANOVA: first step, state the hypothesis. All mu's are the same. H1, not all mu the same. Okay? Step 2, say the decision rule. You find numerator degree of freedom, C minus 1, denominator degree of freedom, N minus C. For a given alpha, obtain the critical value from appendix F for Excel. Yeah. This is appendix F, critical value of F. Okay. In this case, we want the degree of freedom is 3, numerator is 3, and denominator is 16. So numerator degree is 3 and denominator is 16. At alpha 0.05 and 0.85, we see this column 3 and the row 16, we see the number is 3.24. Right, so this is 3.24 here is the critical value of F for 95% confidence level. Okay. So we calculate our test statistics. If it's larger than 3.24, we reject null. If it's less than that, we don't reject null. Okay. And this is the result from Excel ANOVA analysis. Right. For example, here we're comparing station 1, 2, 3, 4, 4 groups, 4 stations. Each has 5 observations. This is their sum. This is the average. This is their variances. And look at the numbers: 242, 246, 228, 226. Are they different or are they similar? Okay, we just find out. Then after you do the ANOVA, you find out that this is between group SSAs here. This is 1914 is an SSE. The degree of freedom here is 3. Why is it 3? Because you have 4 groups, right? 1, 2, 3, 4. 4 minus 1 is 3, right? And the degree of freedom total is 19. Why is it 19? because you have 4 group, 5 each, that's 20 total. 20 minus 1 give you 19. And then this has to be 16 and minus C, because 19 minus 3 will give you 16. How do you get this here? MSA, you take 1479 divided by 3, you'll give this. 1914 divided by 16, you'll give this. And then take 493 divided by 119, give you F 4.121. Right? Remember, the critical value is 3.24. Right? So this is larger than critical value, therefore we're going to reject null. We reject null, we say the averages from different stations are not the same. They are different. Also, you can look at p-values. The easiest way to look at p-values. The p-value is 0.02. Remember, it is less than 0.05, our confidence level. If it's less than 0.05, we say it is significant. So we're saying, hey, the 4 stations, they're not churning out the same type of product, or a product the same quality or same measurements. Okay, and that's a NOVA. Right? Then you make a decision, right? That we just did. You can use the megastat to do the same thing. You can do multiple comparison tests. After rejecting the hypothesis of equal means, we naturally want to know which means differ significantly. We only know that the old means are not the same, right? And in order to maintain the desired overall probability of type 1 error, a simultaneous confidence interval for the difference of means must be obtained. For C groups, there are C minus 1 distinct pairs of means to be compared. And these type of comparisons are called multiple comparison tests. Right? And one of them is called the Tukey's test. Right? We're not getting into the details here. I just want you to know that there are tests available that you can use. It's called Tukey's studentized range test, or honestly significant difference test. It's a multiple comparison test that has good power and is widely used. Right? It's named for statistician John Wilder Tukey. You know, he passed away about 18 years ago. Okay? This test is not available in Excel, but available in Megastat. Okay? The Tukey's test is a two-tailed test. Here we're not getting into details here. This is for your knowledge. If you want to look further, this is the studentized range in Tukey's test. Also, remember, ANOVA assumes that the observations on the response variable are from normally distributed populations that have the same variance. Remember, there's one of the ANOVA assumptions. Right? But how do we know that there's a homogeneity of variances? Right? So one factor ANOVA is only slightly affected by inequality of variance when group sizes are equal. Right? Test this assumption of homogeneous variance, we can use Hartley's test. Hartley's F max test. Hartley's test is named after H.O. Hartley. This is the hypothesis, and the test statistic is the ratio of the largest sample variance to the smallest variance, largest one or smallest one. Okay. We're not getting into detail. There's also Levine's test of homogeneity of variances, and it's more robust alternative to Hartley's test, and it does not assume a normal distribution. So just so you know. Okay, that's all we have for ANOVA. Next topic is Monte Carlo simulation. You probably heard about this from press or from other sources. So what is Monte Carlo simulation, and how can we use that in business applications? Right? We talk about that and talk about the principles behind. We will talk about the 3 examples to give you an idea of this application. Monte Carlo. This is Monte Carlo. This is a casino. There's like a lot of expensive cars, casinos, high roller gambling, And yes, indeed, Monte Carlo is a gambling place, and that simulation actually is derived from those game of chances. Okay? And Monte Carlo, of course, gambling town in Monaco, and the Monte Carlo simulation was first developed in 1947 in the U.S. during nuclear weapons development, okay? And its limited use is limited because of lack of computing power. That's almost 70 years ago. Okay? Then since 1980s, it became more common because we have more computing power in our hand than before. Okay. You can use Monte Carlo simulation in applications such as this tool for managing uncertainty, as for public policy setting, for capital budgeting, for new venture planning, manufacturing planning, marketing planning, quality design, environmental risk, petroleum exploration. You can see it's widely used in many fields. Okay, so what is simulation? Okay. Basically, simulation is modeling a real system to learn about its behavior. Okay? We modeling a real system to learn about its behavior. The model is a set of mathematical and logical relationships. That's why it needs computers to process numbers. You can vary conditions to test different scenarios, because a computer, you can set different levels of different scenarios, and then see what the outcome is going to be. It's in the advantages of simulation is that it is inexpensive to evaluate decisions before implementation, and review critical components of the system. It's an excellent tool for selling the need for change. Right? But there are disadvantages. One of them is that the results are sensitive to the accuracy of the input data. If your input data is not that accurate, not that good, you can't get good results. You've heard about the GIGO principle, GIGO, garbage in, garbage out. Okay? Intelligent agents using secret rules. Okay? And investment in time and resources. You need some time and resources, money to run the simulation. Okay? So what is Monte Carlo analysis? It's a tool for combining distributions, probability distributions, and thereby propagating more than just summary statistics. It uses random number generators, rather than analytic calculations. It uses a lot of random number generations to simulate what's happening in real world. Okay? It's increasingly popular due to high-speed personal computers. Okay? There are some softwares available for Monte Carlo simulation. One of them is called Crystal Ball. Right? It's said to be very user-friendly, it's customizable, can go up to about 10,000 iterations. So, and Gold Sim is another one. Risk is another one. Solver using Excel is another one. So those are the software available you may encounter in your work, in your business, but using simulation. Okay. How are you handling uncertainties? Right? Do you use? See, there are a lot of things that you need to decide before using the system. Okay? Do you use low, middle, or high values? Or do you do what-if analysis? Right? You have multiple what-if scenarios that could confuse as much as enlighten. So it could get really messy and complicated. Okay? Let me give you 3 applications of Monte Carlo situation to give you a taste of flavor of this simulation. First one is estimation of pi. We all know what the pi is, right? Pi equals 3.1415926 535, etc. I used to be able to remember 50 digits of pi. Not anymore, right? Now, what is a pi, right? This pi has something to do with circles, of course, right? And we know if this is a circle, right, the circumference of a circle is found with the formula circumference equals pi times d, that's diameter of the circle, or 2 times pi times radius of the circle. This is a circle, this is the diameter, and there will be the radius. Okay, then you c equals pi times d times equals 2 times pi times r, and then pi equals c over d. Or in other words, pi equals the circle's circumference divided by its diameter. Okay, that's how you calculate, or the definition of pi. Okay, now how do you actually calculate the true value of pi? Remember, this is the infinite number, even the decimal places of numbers for pi. So how accurate can you be? How many digits can you go? Okay? We can use Monte Carlo process to calculate, to estimate pi. Let's look at this example to estimation pi. If you have a circle, let's take a quarter of that circle, it's right here, the blue shaded area of circle. Okay, so imagine you have a big circle, you take half, and then half to half, that's a quarter of a circle, right? Of course, this length here is r, is the radius of the circle. Here is also radius of the circle, right? And this is part of the circle, right? From this radius of r, you can also draw a square like this. Okay, this is a square. The whole thing is a square. Right? So the area of the circle is pi times r squared. We all know that, right? So for this quarter circle, the area of this quarter circle is 1/4 times pi times r squared, right? That's the quarter circle, this blue area here. Now what about the area of the square? Since it's a square, so the area of the square is just r squared, okay? If you use the quarter circle area of quarter circle divided by the area of square, quarter circle divided by square, you will get this over that, r squared will cancel each other, right? And then what you have left is 1/4 of pi, or pi over 4. Okay, so in other words, if we can calculate the area of this circle and also calculate the quarter circle, sorry, and also the area of the square, and then with that ratio we can calculate 1/4 of pi. Of course, times 4 we get a pi, right? So then how do we do that? We can use the Monte Carlo simulation by putting a dot randomly into this, right? We can do them many dots, hundreds of thousands of dots, millions of dots, tens of millions of dots if you want, right? Put many dots, right? Then we can count how many are in the square, right? That represent the area of the square, and how many are in the quarter circle, right? The red dots versus the blue dots, okay? We can do that, right? By doing that, using a random system of Monte Carlo simulation, and do that, you can actually use that to estimate pi. I'm going to let you look at this. As you increase the number of dots, okay, you start with 3,000 dots, 6,000, 9,000, 12,000, 15,000, 18,000, 21,000, 24,000, 27,000, and 30,000. Right? You can see the pi values here: 3.1314, 145, 147, 1428, 1445, okay? And 1436. So as you increase the number of dots, you can see the pi is getting closer and closer to true values. Okay? Monte Carlo method applied to approximating the value of pi. After placing 30,000 random points, the estimation for pi is within 0.07% of the actual value. Okay? This is from message from Mathematica. Okay? Right? There's one application of the Monte Carlo simulation. Let's look at another one. In financial planning or financial investment, investment portfolio for retirement, for example, we invest, you all invest, maybe put aside the savings every month, and then hopefully get a large sum money, when you retire, so you can draw and have a retirement life. Okay, if you have like putting down fixed amount, like $500 a month, and you can have a fixed interest rate, fixed return on interest rate, 7%, then it's deterministic, and then you have a fixed outcome. When you retire after 30 years, you probably get $1.2 million in the account, so you can retire comfortably in Florida or Colorado, wherever you want to go. Okay? That's deterministic. But it could be stochastic. That is, the data, the monthly savings, how much you save every month. It may not be 500. Some days you may save 300. Some days you may say put down 600. Right? The monthly savings is a variable data. And then if that's the case, and also the interest rate may be different, right? And then your outcome you get will not be 1.2 million. You could be all over the place. Okay? So, and in order to simulate what's really happening, we can use a Monte Carlo simulation to estimate that. Okay? You can use some statistics, for example, for monthly savings, right? We can assume on average you save about $500. That's the monthly savings. Right? It's more distributed. You could save as few as 350 a month, or as high as 650 a month. But most chances are you're saving $500, more or less. Okay, that's your savings, monthly savings. And then you say, example of retirement is you save monthly $500. Let's say you have 20 years of time to work, then you retire, and annual growth rate, say, let's say 12%. If that's the case, you multiply compound rate, you get $400,000 upon retirement. But there's uncertainty there, right? You may have to work until 25 years or 30 years, right? Where the growth rate could be as high as 12%, it could be as low as 5%, 7%, right? And then the retirement, value of retirement could be different. So there are all kinds of uncertainties, involved. So then you can use the software allow you to use the different assumptions. They have a distribution gallery. You can use assume normal distribution for your savings, or for using a triangular like this, or Poisson, or binomial, lognomial, uniform, exponential, geometric, Weibull, beta, all others are custom, distributions. You can define that in the system. Okay? And also, as to the number of years to retire, you could take 30 years. You could be like retiring in 15 years, right? That could have a triangular distribution, for example, right? The number of years to retirement. You factor that into your calculation. Okay? And then the annual growth rate, as I said, it could be as high as 15% if you're lucky, and it could be 9% if you're not so lucky. Right? It could have a bell curved log normal. This is actually log normal distribution of the growth rate. You can choose that as part of your retirement example. Right? And then the forecast will be scenario retirement portfolio will be, it could be this could be your outcome, right? This is $600,000 here. The mean is 538, right? You could be as high as $1 million here, or as low as 300,000 something, right? So depending upon the different factors we considered. Okay, so this is a Monte Carlo simulation used in portfolio management and planning. Okay, Let's take another example. There's a Hershey's cake shop, right? The cake seller, Hershey's Cake Shop, sells a random number of cakes each day. Every day they sell some cakes, right? But the manager wants to determine a policy for managing his inventory of cakes. How many cake should he prepare in 10 days? Next 10 days, for example. I don't want to, you don't want to prepare too many cakes, bake too many cakes, not able to sell. Or you don't want to make not enough cakes, so when customer comes, you don't have anything to sell them, right? You want to sell them fresh baked cake, right? Not frozen, hopefully, right? And they do have a demand frequency distribution, right? So they calculated, the chances of having no cakes. So excuse me. 0 cakes sold. There are 10 of them, 10 of those days. Okay, so the probability is 0.05. Okay, out of 200. Okay, and the chance of having one cake sold is 20. The chance of 2 cakes sold is 40. And the frequencies, the 60 days, 40 days. 60 days they have 3 cakes sold. 40 days 4 cakes sold. 30 days and 5 cakes sold. For the last 200 days, they have this frequency distribution. That from historical data, they can have that, right? From this frequency distribution, you can calculate the probability for cakes. The probability for no cake sold, right, is therefore 10. This one here, 10 divided by 200 gives you 0.05. That's the probability. Okay? Probability of having no cake sold in a day, and then probably having 1 cake sold is 0.1, and then 2 cakes sold 0.2, etc. Right, and add together is 1.0. Once you have this data, you can use Monte Carlo simulation to analyze Hershey's inventory. How do we do that? Let's go. You can set up the probability distribution for cake sales. Right, no cake. That's 10% chance probability. 1 cake, 2 cake, 3 cake, 4 cake, 5 cake. Right? You have that historical data. You determine the 5% of the time the 0 cakes were demanded. 10% of the time 1 cake was demanded, etc. Okay? And then you, from the probability distribution, you can set up build a cumulative probability distribution that we have seen before, right? 0 cake, 1 cake. This is cumulative of 0 and 1. This is cumulative of 0 cake, 1 cake, and 2 cakes. This is cumulative of 1, 0, 1, 2, 3, right, etc. All the way up to 100%. You build this cumulative distribution. Okay? And then next, you establish an interval of random numbers, right? You have demand here. This is demand. This is your frequency. This is your distribution. This is your cumulative distribution. And then you set a random number interval, right? In this case, this is a 5%, right? And you want to just use an interval between, say, 1 and 100. So for this 5%, to 1 to 5, right? You want this as the first interval, right? And then from about 5, 6 to 15, you get a second interval, right? From 15. And then the next one from 16 to 35, the third interval. 36 to 65, next interval. And 66 to 85, and 86 to 100. That is 100 here. Okay, so you set a random number interval based on your cumulative probability distribution. Okay, then what do you do? Let Monte Carlo run the numbers. The system will generate some whole bunch of random numbers between 1 and 100. And between 1 and 100, the first number generated is 52. Then 6, 50, 88, 53, 30, 10, 47, 99, 37, etc. Lots of numbers, right? Okay, using these random numbers it's generated, right? Let's see, we'll pick a few numbers. Random number 52, 6, 50, 88, 53, 30, 10, etc. Right? When the generated number is 52, you go to the interval. 52 is in here between 36 and 65. Right? From 52, you go to 36, 65, and then that corresponds to 3 cakes sold. And they put 3 here. Okay, the 52, 3 cakes sold. When the random number is 06, where do you go? 06 is right here. 06 and 15, you got 1 cake sold, so it's 1 here. When generated random number is 50, where is 50? Again, 50 is here, so it's 3. When the general number is 88, where is it? It's here, between 86 and 100. So 88, you have 5 cakes sold, etc. Right? So by using these random numbers, you can create a random demand, simulated demand. 3 cakes on this day, 1 cake, 3, 5, 3, 2, 1, 3, 5, 3, etc. That's how you use that to estimate, random demand, on your cake. In fact, you can also use computers to create a lookup table using cumulative probability. You generate random number and look up in the table. You do the exact same thing as we just did. Okay? You calculate the simulated demand, just like here, simulated demand. 5 cakes on day 1, 3 cakes on day 2, etc. Okay?